Imagine stepping onto a plane that doesn't roar with the sound of burning jet fuel, doesn't leave behind trails of carbon emissions, and yet can fly more than 400 miles on a single charge. For years, that idea sounded like a fantasy, something that belonged to sci-fi movies rather than real-world airports. But in typical Tesla fashion, the company decided that impossible was just another engineering problem waiting to be solved. The real question now isn't whether Tesla's super-electric plane can exist, it's how they made it possible. What kind of design, technology, and innovation could make a fully electric aircraft not only feasible, but superior to today's regional jets in both efficiency and performance? The answer, as we're discovering, lies in a mix of physics, materials, science, and Tesla's signature approach to doing everything differently. When Elon Musk first hinted at electric aircraft nearly 5 years ago, many shrugged it off as one of his bold daydreams, a headline grabber, rather than a blueprint. The idea of a plane powered by batteries seemed absurd given how energy-intensive flight is. Yet, 5 years later, Tesla's concept has evolved from theory into a working reality that's starting to take physical shape. What once sounded like an impossible claim has become a meticulously engineered machine designed to prove that clean. Aviation can be faster, cheaper, and more efficient than we ever imagined. Tesla's upcoming super-electric plane is the culmination of years of research, battery breakthroughs, and aerodynamic refinement, promising not just flight, but an entirely new way of thinking about air travel. It's designed to deliver a 400-mile range per charge and an astonishing 12-minute turnaround time between flights, completely redefining what ready to fly means. At first glance, you might assume this plane borrows ideas from conventional designs. But look closer, and you realize nothing about it is ordinary. Tesla's engineers have gone back to the drawing board, rethinking not just how planes move through the sky, but how every square inch of their surface interacts with air, moisture, and drag. The first secret to its range lies in its skin. The body of Tesla's electric aircraft isn't made from standard aluminum or riveted metal sheets. Instead, it's built from a single-piece composite fuselage, an ultra-strong and ultra-light shell formed using Tesla's perfected gigocasting techniques, similar to how they revolutionized car manufacturing. This structure is then coated with a hydrophobic nanolayer that actively repels dust, moisture, and debris. The smoother the skin, the less drag a plane experiences, and drag is the invisible enemy of every aircraft's efficiency. On smaller aircraft, skin friction alone can account for nearly half of all drag losses, by nearly eliminating joints, seams, and rivets. Tesla's engineers have achieved a surface that's so smooth it almost glides through air like water over glass. That might sound like a small improvement, but every tiny reduction in drag means huge gains in range. Even a 5% decrease can translate to dozens of extra miles in the air. Tesla's design reportedly cuts that friction by up to 10%, effectively giving the plane a free-range boost without adding a single new battery cell. But it doesn't stop there. The wings, long, slender, and beautifully tapered, tell another part of the story. They're designed with an extremely high aspect ratio, meaning they're longer and narrower than those of conventional planes. The result is a significant drop in what's known as induced drag, the resistance that occurs when air spills around the wingtips. By extending the wingspan and adding sculpted winglets at the ends, Tesla reduces this effect by nearly 30%. The result? Less wasted energy, smoother flight, more distance covered per watt of power. The landing gear, too, has been given the Tesla treatment. Instead of bulky external struts, the landing gear is fully retractable and sealed inside flush aerodynamic bays that close completely once the plane takes off. The entire underbelly becomes a smooth aerodynamic surface, eliminating turbulence that typically forms beneath traditional aircraft. These small, almost invisible design tweaks combine into something extraordinary, an aircraft that slices through air with minimal resistance, giving Tesla's electric motors and batteries a far easier job to do. But what truly defines Tesla's electric plane isn't just its shape, it's the way it's powered. Traditional jet engines burn kerosene and throw massive amounts of energy out the back in heat and noise. Tesla's distributed electric propulsion system does the opposite. Instead of two giant engines hanging under the wings, this plane features multiple small high-efficiency electric motors spread across its wingspan. Each motor directly drives a ducted fan. All of them are coordinated by Tesla's onboard AI flight computer, which continuously adjusts thrust from each motor in real time. This setup provides exceptional balance, instantaneous response, and redundancy. If one motor fails, the others automatically compensate, maintaining stable flight. It's a safety and efficiency improvement rolled into one elegant solution. Electric propulsion also means no combustion, no emissions, and far less noise. Imagine standing near a runway and hearing only a soft worry hum instead of a deafening roar. Airports that currently restrict night flights due to noise could operate Tesla's electric planes around the clock. The implications are huge, not just for travelers, but for entire city infrastructures. Short-haul and regional air travel could become as quiet and clean as taking a train. Underneath this quiet elegance lies the real powerhouse: Tesla's belly-mounted cassette battery system. Instead of packing batteries into the wings or fuselage permanently, Tesla's engineers have developed modular battery packs that can be quickly swapped or recharged using ultra-high power connections. Each cassette fits snugly into a structural bay under the aircraft's floor, serving both as an energy source and as part of the plane's load-bearing structure. When the plane lands, ground crews can slide out depleted cassettes and replace them with fully charged ones in minutes, achieve in a complete turnaround in as little as 12 minutes. That's faster than refueling a jetliner and reboarding passengers. Tesla's megacharger infrastructure, which already supports its semi-trucks, will be adapted for aviation, providing up to 1.2 megawatts of power per connection, allowing ultra-fast recharging and seamless energy management. The batteries themselves are rumored to use Tesla's next-generation aluminum-ion and solid-state hybrid technology, offering nearly twice the energy density of current lithium-ion packs with improved cooling and safety. Aluminum-ion chemistry allows rapid discharge without thermal runaway, meaning the plane can deliver massive power during takeoff and climb without overheating. At cruising altitude, where energy demand is lower, the system automatically switches to high-efficiency mode, maximizing flight range while minimizing stress on the cells. Add regenerative braking during descent, and Tesla's engineers claim the plane can recover up to 5% of its used energy in unprecedented feat in aviation. The aircraft's software is just as advanced as its hardware. Tesla's onboard flight AI continuously analyzes airflow, temperature, battery health, and power distribution, making micro-adjustments hundreds of times per second. It optimizes everything from propeller pitch to wing surface deflection, ensuring the smoothest and most efficient flight possible. In essence, the aircraft is constantly teaching itself to fly better. Each flight's data is uploaded to Tesla's central neural network, where machine learning algorithms process millions of data points to refine performance for the next flight. This continuous feedback loop means every Tesla plane in operation gets smarter over time, just like Tesla cars do with autopilot and full self-driving. Safety, naturally, is another pillar of Tesla's design. With multiple redundant power systems, distributed motors, and modular batteries, the plane is far less vulnerable to catastrophic failure than conventional aircraft. Even if one or two motors were to fail mid-flight, the AI could redistribute power to maintain stability and safely continue or land. Emergency glide efficiency is also higher thanks to the ultralight composite body and long wings, allowing longer glide distances with less altitude loss. Tesla's engineers have also included a ballistic parachute recovery system for smaller versions of the aircraft. It's giving an added layer of safety in case of total power loss. Inside, Tesla has reimagined the cabin experience with the same minimalist sophistication seen in its vehicles. The interior is quiet, spacious, and built with sustainable materials, lightweight carbon fiber panels, vegan leather seating, and panoramic smart windows that automatically tint based on sunlight and altitude. Each seat includes integrated ventilation and personal climate control, powered directly by the aircraft's low-voltage system. The cabin lighting adapts dynamically to reduce jet lag, syncing with destination time zones. Passengers can access real-time flight data, entertainment, and even Tesla's signature AI assistant through their seat screens or mobile devices connected via Starlink Wi-Fi. There's no need for heavy onboard servers, as everything is streamed and processed through the cloud, minimizing onboard weight. The cockpit, too, is a vision of the future. Traditional dials and analog gauges are replaced by dual panoramic displays, powered by Tesla's custom flight OS. The system supports semi-autonomous flight, handling takeoff, cruise, and landing with minimal pilot input. In time, this may evolve into full auton